All right, we're going to finish this this chapter by looking at higher derivatives. And so here's sort of just a motivating exercise. Let's say we've got a function, a nice simple polynomial, 5x cubed minus 2x. Well, let's find y prime. Right, we call it y prime, or we could write dy dx. And this is using the power rule. We get, what, 15x squared minus 2. Now, this is a function in and of itself, right? 15x squared minus 2. And maybe I want to be able to determine how that function is changing. It's a function of x. I can take its derivative. So if I take the derivative of the first derivative, right, we call this the first derivative, then we get what we call the second derivative. And we'll denote the second derivative with the y double prime. So we make two of those tick marks. And if in the dy dx notation, we have d squared y over dx squared. Notice the little superscript is in a different location. So up top, we take this to mean differentiate twice. And the superscript on the bottom here is on the x, meaning with respect to x both times. So when we take this derivative of 15x squared minus 2, we get 30x. That, of course, is 30x. That, of course, is also still a function of x, so we could take its derivative and get the third derivative. Which is just 30, and if I take the derivative one more time, it's the fourth derivative. Now, by the time we get to the fourth derivative, we stop writing tick marks because you just sort of are swimming in a sea of tick marks. And what we do is we write as a superscript 4 in parentheses. The parentheses are really important, otherwise it's just an exponent, and that's not what we mean. And then we get 0. Of course, the fifth derivative is 0, and the sixth derivative, right? As soon as we get to 0, you just keep taking derivatives. All the rest of them are going to be 0. If you start off with a polynomial like we did, we had a polynomial of degree 3, then you will eventually, if you keep taking the derivative, you eventually get to 0. If you have a polynomial of degree n, there will be precisely n non-zero derivatives, and you'll notice that we had 3 non-zero derivatives, so we got 0 once we got to the fourth derivative. So let's do an example. You know, the last one we were talking about how when we had a polynomial and you keep taking derivatives, you'll eventually get to 0. That's only true for polynomials. And when you see an exercise or a problem that's written like this, where they don't say find the second derivative, they don't say find the first, second, and third derivatives, they say find the higher derivatives. That means all of them, and they only ask that question if what you have is a polynomial. And this is a polynomial. Now, it's written in factored form, but if we, you know, expanded out the product, it would be a polynomial of degree 5, right? Here we're squaring an x squared, so there's an x to the fourth, and then we're multiplying by x, so that would be an x to the fifth. Now let's begin. Let's take the derivative by using the product rule. So f of x, the given function, is x times x squared minus 1 squared. So for the first derivative, if we use the product rule, we have g times f prime. So I'm just going to write out what we get here without doing the side work this time. Usually I write that out. If you want to do that, maybe pause the video, kind of get yourself set up. When we do that, let's see what we get here. G times f prime, the derivative of x is 1, plus f, that's just x, times g prime. And so we've got to use the general power rule on the parentheses squared. So that's 2 times x squared minus 1 just to the first, and then the chain rule says times 2x. So we need to clean this up a bit. I'll note that we can actually factor out an x squared minus 1. to the first power. So let's do that. And when we do that, what's left inside is x squared minus 1 to the first plus, let's see, we need 2 times x times 2x, that would be a 4x squared. So x squared minus 1 times 5x squared minus 1. So this is the first derivative. Now, we could take the second derivative by using the product rule. I'm going to go ahead and just do a little algebra. I mean, at this point, it seems like we could just expand out this product, FOIL it out, and then we have a nice polynomial, and then taking the derivative will be real easy. So I'm going to, this line is still the first derivative. I'm going to FOIL this out. We get 5x to the fourth. Let's see. Minus x squared minus 5x squared is minus 6x squared plus 1. So there's our first derivative. Now let's take the second derivative. We get 20x cubed minus 12x. And that's that. The third derivative is 60x squared minus 12. The fourth derivative is 120x. The fifth derivative is 120. And now the sixth derivative is where we get to 0. And so the way I'm going to write this, because it's the sixth derivative that's 0 and all the rest of them, right? The seventh derivative, the eighth derivative. So I'm going to write that this way. I'm going to say the nth derivative of x is equal to 0, where n is greater than or equal to 6. And here's all of the derivatives of the given function. Okay, so let's do another example. They want us to find f double prime of -2 for this function. So the first thing we need to do is set about finding the second derivative. I'm going to rewrite this function. And I'm going to rewrite it in a power rule friendly form. So I got 2 times 1 minus x to the minus 1. And that means now I don't have to use the quotient rule. So it's kind of convenient. The first derivative, using the power rule, bring down the minus 1. So we get a -2, 1 minus x to the minus 2 power. And then the chain rule would have us multiply by -1. So I'm going to just simplify this a bit. 2 times 1 minus x to the -2. That's the first derivative. For the second derivative, this is already in a nice power rule friendly form. So I'm going to bring down the -2. We get -4 times 1 minus x to the -3rd power. And again times a -1 for the chain rule. And we get +4. And I'm going to write this, because we're going to evaluate it, I'm going to write it without negative exponents. So 4 over 1 minus x cubed. There's our second derivative. And now let's plug in -2. And that gives us 4 over 3 cubed is 27. Now, before we do the next example, I'm going to do a second example here. It's going to be related. We could call it example 2.38b. And in this example, we're going to just find the second derivative. But this time, the function that they give us is 2 over 1 minus x squared. All I'm doing, the only difference, is that it's a 1 minus x squared in the bottom. So the way we're going to find the first derivative, you know, like it's still a fraction where there's no variable up top, so we don't have to use the quotient rule. Let's rewrite this in a power rule friendly form. Okay, so now when we find the first derivative, we're going to bring that negative 1 down, so we have a minus 2, 1 minus x squared to the negative 2 power. And now when we apply the chain rule, now is when things are different. We're going to multiply by negative 2x. And I'm going to just clean this up a little bit, so we have positive 4x, 1 minus x squared to the negative 2. So here's the first derivative. And it's in a good form now to just take a derivative again, but what I want to point out is this is a product. When we find the second derivative, we have to recognize that, oh, it's not exactly the same situation as when we were finding the first derivative. Now we have a product rule because we introduced a factor of x, right, when we applied the chain rule. So it's important once you find the first derivative to just assess that function fresh, like it's its own function. Assess it, figure out what you need to do to find its derivative. So that's a product rule. Our f function is 4x, so f prime is 4. Our g function is 1 minus x squared to the negative 2. And so g prime is minus 2, 1 minus x squared to the negative 3 times a negative 2x. So positive 4x, 1 minus x squared to the negative 3. There's our g prime. So let's put this together. G times f prime, right? We're going to multiply those two. So that's a 4 times 1 minus x squared to the negative 2. And then f times g prime, I'm going to multiply those two together. And when we do that, we're going to get 16x squared, 1 minus x squared to the negative 3. And then at this point, you know, we could simplify, right? We could take out a 4 and 1 minus x squared to the negative 3, because that's the least power. And inside we have 1 minus x squared plus 4x squared. And I'm running out of space here, but this is going to look like on top 4 times the stuff in the brackets simplifies to 3x squared plus 1, and in the bottom 1 minus x squared cubed. There's f double prime in this case. So, you know, what I really wanted to point out, the reason I wanted to do this example in addition to the one that came before it, is just to highlight that after we found the first derivative, we had to recognize that, oh, you know, we introduced this factor of x. We have to use the product rule. In the first one, in the given function, the same technique worked twice just as well, right? We didn't have to worry about the product rule when we took the second derivative. All right, so with higher derivatives, really, we're not learning new differentiation techniques here, right? We're just learning what we mean by second derivative and third derivative, right? And that we can keep taking derivatives of functions. But if you want to take something and then make it a little bit more interesting, it's always good to do an implicit function problem. So we're going to find the second derivative of y with respect to x for this function. This function is implicit. It's an ellipse, right? It's both variables are squared, and the coefficients are different. So here's the equation. We're going to start this process much like we do when we find the second derivative of the other functions. We're going to start by finding the first derivative. So let's differentiate with respect to x. When we do that, we get 4x plus 6y dy dx equals 0. Notice those coefficients are both even. I'm just going to go ahead and divide by 2. So we have 2x plus 3y dy dx equals 0. Now I'm going to do a little bit of side work here to solve for dy dx. If I rearrange that equation, we get 3y dy dx equals a negative 2x. And then we just divide by 3y. Right, so here's an expression for the first derivative. Now you could take this and say, oh, I'll differentiate this to find the second derivative. I'm going to go about it a slightly different way. I'm going to take this equation over here, right, the equation we got after we differentiated, and I'm going to differentiate again with respect to x. When we do that, we have to recognize that this is a product. So let's do some of that side work. The f function here is going to be 3y. So f prime is 3 dy dx. The g function is dy dx. Now, think about this. Think about what g prime should be if g is dy dx. So g prime is the derivative of g. So the derivative of dy dx, well, that's the second derivative. That's d squared y dx squared. Alright, so now coming back over here to the left, when we take the derivative again, we get 2 plus, now applying the product rule, g times f prime. So we are multiplying those two together, and when we do that, we get 3 times the square of dy dx. Plus f times g prime. We're going to multiply these two together. That's 3y times the second derivative. And then on the other side, the derivative of 0 is still 0. So here we have this equation. You'll notice that the second derivative is in this equation, and we want to solve for it. But if our original equation can be expressed just in terms of x and y, and the first derivative can be expressed just in terms of x and y, then when we find the second derivative, it should be able to be expressed just in terms of x and y, meaning not in terms of x and y and dy dx. So, we have dy dx showing up here, and we're going to just make a substitution. So plugging that in, we have negative 2x over 3y. That's all squared. Alright, now we're going to do some algebra. I'm going to square out that negative 2x over 3y. So that's 4x squared over 9y squared. Positive, because we're squaring it. And we could isolate the second derivative, but what I'm going to do first, I think, I'm going to do a couple of things. One is, I'm going to reduce this fraction, so 3 goes into 9 3 times. And before I isolate the second derivative, I'm going to look at this and just say, well, we've got this equation with fractions. I'm going to clear denominators first. I think that'll just make it a little simpler. So I'm going to multiply both sides by 3y squared. On the left side, we're going to have to distribute the 3y squared to all terms. So when we distribute to the first term, we got 6y squared. When we distribute to the second term, it'll cancel the 3y squared that's in the bottom, so that's 4x squared. And then when we distribute to the last term, we'll have a 9y cubed times the second derivative. And on the other side, we've got 0. So now I think we're in a much better position to isolate that second derivative term. We'll subtract 6y squared and 4x squared so that we get 9y cubed times the second derivative is equal to negative 4x squared minus 6y squared. And then we divide. So it looks like we're almost done, and we are almost done, but look, something really cool is about to happen. Up top, we have a common factor of 2. In fact, I'm going to go ahead and take out a negative 2. And then we have 2x squared plus 3y squared. This is all over 9y cubed. So it looks like, you know, we have our second derivative, and this is equal to the second derivative, but we could simplify this in a really clever way. Let's look back at the original equation they gave us, right? This equation is the universe in which this problem exists, right? The premise of this whole problem is that 2x squared plus 3y squared is always equal to 6. So if we see the expression 2x squared plus 3y squared show up, we can replace it with 6. And that's exactly what we have here. In this problem, that expression is always equal to 6. So this is negative 2 times 6, negative 12 over 9y cubed, and we could actually reduce that. 3 goes into 9 and 12, so we got negative 4 over 3y cubed. And that is the second derivative. As it turns out, the second derivative, the value of the second derivative, depends only on the y coordinate on the ellipse and not on the x coordinate.